Alright, so in the last set of videos, I talked about light and how the visible light that we see with our eyeballs isn't the only form of light there is. The electromagnetic radiation that visible light is a part of is only a small, the electromagnetic radiation that visible light is only a small part of is really actually pretty vast, and includes radio waves, infrared waves, X-rays, etc. So the point of these videos is then, now that we know that all of these light forms of electromagnetic radiation are that they exist in our universe, how can we use those to learn about space? Because that's really all we've got. Um, so far, we've been able to return samples, actual rock and soil samples from the moon. Very close uh, body to us in this vast universe. We haven't even been able to return samples from Mars yet. The best we can do is actually send probes there with devices that can analyze soil and then send those analysis results back. But even at this point, we're really just starting to develop um, complex rovers that can move around Mars pretty easily and carry lots of different instruments. But they're pretty basic. If we were to actually be able to send humans there to study rocks, we would learn about Mars much more quickly. Long story short, um, we can't even bring back real samples from the closest planet. So how are we expected anytime soon to go to the closest star and see what's going on there? But luckily we have an alternate source of data, and it's through light. Light can travel through space. It travels very fast, although, as we're learning, the universe is so extremely ginormous that even at the speed of light, it takes long time for that light to reach us. Um, so anyway, let's start talking about how we can use that light to actually figure things out about our universe. And so, the first thing um, we do with light, we use with light, is to separate the light into its different wavelengths and analyze the types of light we get from the source. So that's called spectroscopy. So we can bend light, like as you see here in the prism. It's bending white light, which contains basically all the wavelengths of visible light, where this is refracting it, bending it into the different wavelengths. You can also use diffraction, which is another way of bending. Um, in the lab that you either did or will do soon, um, that was using a diffraction grating to bend the light. And here's some examples of that. Some of the tubes he uses in here are tubes we don't use. So just a quick little viewing. So here's hydrogen gas, and you can see this diffraction grating um, bends the light into its different colors. And hydrogen gas doesn't give off light. Heated hydrogen gas, as you can see here, doesn't give off light at all the wavelengths. So it's not pure white light. We also got helium, which you can see, at least in his, has more lines than ours shows. What else we got? Yeah, the spectral lines are the fingerprints, so I'll talk more about that. We got mercury, which we don't use, pretty dangerous to have mercury gas. It's cool. So that's using a diffraction grating to bend the light. And then you can use a prism to bend light. And you can see here there's a white light source behind this prism, and it's spreading it out into the rainbow of colors. And as we learned, there's probably some infrared light here that we can't see, and some ultraviolet light that we can't see. It's pretty cool. So we can bend the light and learn a lot about about things that we will most likely never be able to visit and touch and analyze in person. Um, oh yeah, this is another example of light refraction through raindrops. They act kind of like prisms. You can get the beautiful rainbow. And as you can see in this diagram, it's not just visible light that can be bent and spread out. It's all forms of light. So if you use things like a crystallized molecule and you shine an X-ray beam on it, that molecule could diffract the light rays and bend them different amounts, and so you can actually um, see a property of the X-ray beam using this crystallized molecule. So it all starts with the fact that all objects give off light, and light, a photon of light, is given off. This is going into basically electromagnetic, the branch of physics that studies electricity and magnetism. And just to, we're not going to study this in this class, but just to give you the brief picture, if charged particles move or accelerate, then that can be electrons primarily, and also protons, but primarily electrons. As they accelerate, they give off a photon of light. That's just a property of nature, and it's these photons of light that are electromagnetic radiation. So all objects, you, me, um, the chair you might be sitting on now, or the floor you're standing on, anything gives off light because everything contains electrons that are bumping into each other and accelerating. Some objects don't give off what's called blackbody light, meaning light at all wavelengths. Some objects do, as we're going to learn the difference between the two. Stars, though, do give off light almost like a black body. So what is a black body? A black body is an ideal object that gives off light at all wavelengths. I'm not going to go into the nitty-gritty details about it, but basically you can, if you look at this graph here, you got intensity, which is brightness of light, and you got frequency, which is essentially the spectrum, the different wavelengths. So you might start with radio down here and go to like microwaves here, maybe infrared, visible light, etc., all the way up to gamma rays. So that's what the x-axis is. A black body will give off light in essentially all of those frequencies. It, of course, depends on the temperature of that body. The sun and other stars approach that. You can see this is the actual light curve given off by the sun, and you get some other little bumps and curves in here, which come about because of objects between us, like the Earth's atmosphere and the sun's atmosphere. But stars do give off light at just about all wavelengths. So that's why, for example, our sun, which is about 5,800 to 6,000 degrees at the surface, would be a curve somewhere between these two. If you follow my pointer, something like that. So you can see it definitely gives off visible light, which is why we can see the sun, but it also gives off infrared and microwaves, radio waves, and ultraviolet, maybe some X-rays. Not really gamma rays. It's not hot enough at that point to give off gamma rays, or a significant amount of gamma rays, unless there's a solar flare, which can be really hot. But you could see if this curve were to go up, it would also be going over and eventually reach the gamma ray part. But so yeah, our sun gives off all of these, including visible light. In fact, our sun, the peak intensity, peak brightness of the light given off is in the visible, which is kind of cool. Whereas a cool object like you or I is cold enough so that the rightmost wavelengths of light don't even approach visible, which is why you or I don't glow. We don't give off visible light. If we did, we could see each other in the dark with our eyeballs, but we can't. But we do give off infrared, and so that's what's going on. It's kind of interesting. If you look at a stove, like the element on the top of a stove, you might use to boil a pot of water. If you shut the lights off at night and look at the elements when they're off, you don't see anything. If you were to look at them with infrared goggles, you might see something. But then you turn on the burner, it gets hotter and hotter, and so this curve gets closer and closer to these curves up here. Eventually, right down here, it's going to start to, when it gets hot enough, start to give off red light, which is why they glow red first, the burners on your stove, because they're reaching a temperature high enough so that they can give off red visible light, so you could actually see them. So that's what's going on here. How can we use this in space? Well, different objects are at different temperatures, so you can use it to tell the temperature. You can use it to tell a bunch of different things. Really hot objects, high energy objects, will give off some visible light, but if you analyze them in the ultraviolet or the X-ray, you'll see more intense light from those wavelengths. You can actually take pictures of objects at all the different wavelengths and combine them to get an overall picture of what the object is doing. In the last videos, I showed you different pictures of the sun at different wavelengths, and you could see the different aspects of it. So yeah, a star like our sun is giving off a continuous spectrum. What that means is it's giving off light at every single wavelength within reason. You know, again, like I said, our sun isn't hot enough to necessarily give off gamma rays consistently. So, but within the wavelengths that it does give off, it gives off continuous, which is why we should see like an uninterrupted visible part of the spectrum. But what do we see? We see this. We see gaps and holes in the continuous spectrum. Something is going on here. Why are there gaps? It doesn't look very continuous, right? Well, this is called an absorption spectrum. So here's our sun, and it's giving off a continuous spectrum. But between us and the sun, there's other stuff like cool gas in our atmosphere. There's actually material in the sun's atmosphere that block the light coming from the sun. And then, excuse me, and then when we look at the spectrum of the light, some of the light coming from the sun is blocked by this cool gas and doesn't reach us, so we see darkness. These lines are actually blocked light, and actually these lines depend on what the gas is made out of, and I'll talk more about that in a second. So that's an absorption spectrum. Light from the star is being absorbed, and we see small gaps of light. Alright. Well, so I just mentioned that depending on what the gas is made out of, it will depend on which lines are blocked, right? Well, let's say the gas is made out of hydrogen. Which lines will it block? Well, it'll block the lines that you saw when you looked at the hydrogen gas in the spectroscopy lab. And that's called an emission spectrum. So if you have a heated gas, heated somehow, and you look at the light coming just from that gas, then you will see mostly darkness with gaps of light, little bands of light. That's what these things are here. So hydrogen, for example, you see a nice line in the red, a nice line in the blue, and purple, and violet, etc., etc. So this gas only gives off light at very specific wavelengths. It's like a fingerprint. So hydrogen gas will always give off these lines. So so what do we got here? For hydrogen we got red, sort of like cyan blue, and a couple purples. So if you look here, here's like a red gap missing, and there might be a cyan one missing, and a couple purples. There's actually a lot more. You might be able to say that hydrogen is one of the gases that is blocking or absorbing some of the light from the sun. So we're approaching 15 minutes, so I'm going to actually continue that in the next video. But suffice to say that the absorption lines that you see here will be the same as the emission lines if the gases or the elements are the same. I'll talk more about that in the next video.